give you a brief recall of what we had covered in the first 1 hour class this week, and then I'll move on with the continuation of what we had covered in the last lecture. So we basically started with the initially we started with the zero dimensional defects, in which we looked into point defects and different kinds of point defects, including vacancy, interstitial, and substitutional items. Then we started with one-dimensional defects in this week's first class. The line defects are also known as dislocations, and we looked into two kinds of dislocations. So I'll be recalling that. Then we'll move on towards the area defects, which includes grain boundaries, and we'll look into bulk defects, which are pores and cracks. So in the line defects, we had two kinds of line defects that were there that we discussed: the edge dislocations and the screw dislocations. As for the edge dislocations, we said that it's basically a defect in which you can easily visualize the defect as an extra half plane of atoms in the lattice. And here was the extra half plane that was inserted within the lattice, and it could be easily visualized. Then we said that this is the extra half plane that has been drawn for you. Then we said that this edge dislocation is called a line defect because the locus of defective points produced in the lattice by the dislocation, they lie along a line. So here is the line along which the locus of defective points they are centered, and that's why this defect is referred to as a line defect. Furthermore, it stated that line runs along the top of the extra half plane in this situation, as the plane is inserted from the bottom, so it is the top of the extra half plane through which it is running. Uh, it further says that the interatomic bonds are significantly distorted only in the immediate vicinity of dislocation line. So if you looked at the bonds situated within this region, it is essentially the distortion of the bond that takes place in the vicinity of the dislocation uh, line. Furthermore, we looked into the notation of how to specify the edge dislocation, and we said that if the plane is inserted from the bottom, if the plane is inserted from the bottom up till the point where the plane is inserted, you block that with a T, and this T is the nomenclature for an edge dislocation for a plane which is inserted from the bottom. If the plane is inserted from the top, you'll have an inverted T to identify the edge dislocation. And then we looked into the measure of lattice distortion, which is represented by B or slip or Burgess vector, and we said that we'll move around the dislocation line one complete movement along the dislocation line with equal number of steps. The last step to complete the uh, or to close the loop would basically give you the measure of lattice distortion or Berger vector. So the displacement vector that closes the loop while traveling equal number of uh, lattice steps around the defect is basically something that would give you the extent of dislocation that is there within the lattice. Then we had this uh, point that Burgess vector is essentially perpendicular to the dislocation line. If you look at the dislocation line and the Burgess vector relationship, they are essentially perpendicular for an edge dislocation, and we said that the region in which the plane is being inserted is essentially in the compressive strain, and the region where the plane is missing is essentially the region where you have tensile strain as a result of edge dislocation. All right. Then we looked into screw dislocations, and we said that screw dislocations are slightly more difficult to visualize due to the nature of it. So we had this uh, block of metal in which we applied shear stress on one corner of the block, and as the shear stress was applied, it was seen that the metal started to rip apart. So the action of this shear stress at this corner was that the metal started to rip apart. And when we looked into the uh, plane that is essentially this plane, the plane which is ripping apart the top surface of it, it appears that these red atoms are the atoms that have moved one atomic distance. The blue atoms are the atoms that are still situated at their original position, and the green atoms are in the process of moving towards one lattice step. So this is what we looked into, and in order to visualize discrete dislocation, we said that we'll draw a line that will pass through the dislocation point, and if you see behind this, there is the lattice still at its original position. In front of it, there is a dislocation that has already been created. And in order to find out the effect of this or magnitude of this dislocation, you'll again move around in a loop around the dislocation. So you moved around in a loop in the dislocation, and you found out that this is the Burgers vector, which gives you the extent of dislocation in case of screw line defect or screw dislocation. And you see that in case of Burgers vector, the dislocation is essentially the Burgers vector is essentially parallel to the dislocation line, and this basically curved arrow is indicating the dislocation, screw dislocation, the notation for screw dislocation. B is parallel to dislocation line. This is what we had covered in the last lecture. Is there any question regarding this, what we had covered in the last lecture?
No, sir.
No,
All
sir.
right. All right. So if we have no questions regarding what we had covered in the last slide, we'll look into the dislocation motion, how the dislocation moves. We are looking into the edge dislocation movement. So you have this lattice over here at this location A. If you could see, there is an extra half plane that is present within the lattice. And if the shear stress is being applied onto this lattice, if this is the stress that is being applied onto this lattice, you have this dislocation, edge dislocation present. This is edge dislocation, and this is the plane which separates the presence of an extra half plane. So there is a plane present over here, and there is no plane present over here. So this is the plane that is separating the edge dislocation, uh, the presence of edge dislocation in the lattice. Now, if we apply uh, shear stress onto in this direction onto this lattice in this direction, what would happen? Dislocation moves a small amount at a time. What would happen would be that the dislocation in the top half of the crystal is slipping one plane at a time as it moves from right. So the dislocation which was originally located at A is has now moved to the point B due to the application of the shear stress. These bonds have disrupted, and they have been created with these the atoms at position A, and now the dislocation has moved to a new position which is B. And where has this moved? The dislocation has moved along the slip plane. Is this point clear to you?
Yes, sir.
All right. Now, eventually what would happen? Eventually the top of the crystal would move with respect to the bottom half. The top half of the crystal would move with regards to the bottom half. How? You would see that eventually the dislocation would move from A to B, then jump from B to C, C to D, and then to an position where you'll have a unit step of slip present within the lattice. So you'll have an extra half step present on the top plane. It is as if the top plane, the top of the crystal lattice has moved with regards to the bottom half of the crystal along this slip plane. And the important thing is only a small fraction of the bonds are broken at any given time. It is not as if all the bonds are broken at any instance, and they are created at another instance. What has happened is that the bonds kept on breaking in smaller steps, so that the movement in this manner requires much smaller force than breaking all the bonds across the middle place simultaneously. So this is an ease that is associated with edge dislocation, that uh, small amount of force is required to make the dislocation move or slip along the slip plane. Thirdly, the important thing is that the edge dislocation, it moves parallel to the direction of stress. This edge dislocation is moving in a direction which is parallel to the direction of stress. In order to have a clear view, let us have a look at this image. This is your extra half plane. This is the dislocation line on the top of extra half plane. And when the shear stress is applied in this direction, the dislocation plane would move in the direction which is parallel to the shear stress until and unless a complete step is being achieved. So the edge dislocation, in edge dislocation, the movement of dislocation is parallel to the direction of the stress. All right.
Yes, sir.
All right. Now, in order to have a better view of how the edge dislocation is moving, uh, or edge dislocation moves, let us have this extra half plane. This is an extra half plane that is being inserted in the lattice. Now, recall the movement of this extra half plane or edge dislocation within the lattice. See how it moves. Upon the application of shear stress in the lattice, you will see this dislocation moving in steps. So it moved from this it moved from this position to the new position over here, and it moved to a new position over here, again to this point, this point, this point, and ultimately the dislocation converted into a complete unit cell step. All right. So this is how an edge dislocation moves in the lattice upon the application of shear stress. Now, with regards to the screw dislocation, you have the shear stress being applied in this direction, and if you see, these are the atoms at their new position, these are the atoms in the movement, these are the fixed atoms. In screw dislocation, the screw dislocation will move upward in the image, which is perpendicular to the direction of stress. So if this is the direction of stress, the screw dislocation is essentially moving in this direction, which is perpendicular to the direction of stress. So this is your screw dislocation. This is the screw dislocation line. And if you see this dislocation, the direction of this dislocation line or the movement of this dislocation line, if this is the dislocation line, it is moving in this direction, which is perpendicular to the direction of stress until a complete step is being generated. Clear enough?
Yes, sir.
All right. Now, this is the schematic representation. So if you see this atom has moved to the new position, or these atoms have moved to the new position. If you look at these golden or yellowish atoms, they are these three atoms, they are in the process of movement. They have not acquired new positions, they are in the process of movement. And these are essentially located at their original position at the moment. As the stress is being applied, you see another atom has moved to the new position, and these three now become the atoms which are in the process of movement. Similarly, if you continue, now this atom has moved to the new position, and the next three atoms, they are in the process of movement. Continue with this. First four atoms have moved to the new position, and the last three atoms, now they are in the process of movement. The process continues until you have a complete unit cell step that the lattice has moved as a result of the application of shear stress and the movement of slip dislocation. So the stress was essentially applied in this direction, and if you see, the dislocation has moved from this point up till this point, which is essentially perpendicular to the direction of applied stress. Is this point clear to you guys?
Yes, sir.
All right. So what I'll do is